Hi, this lecture is about transformers. So what is a transformer? The transformer is an electrical device which is operating on the concept of magnetic coupling. So what do you mean by magnetic coupling? When you have two inductors placed near each other, the flux present in one inductor will link with the other inductor, and because of the flux linkage, there will be a voltage induced in the second inductor due to the Faraday's law of electromagnetic induction. So this is what is called the magnetic coupling. So when we have magnetic coupling, there will be minimum of two coils here. So we have coils coupled magnetically. So magnetically coupled coils will be somewhere like this. You have a coil here, one coil, and there will be another coil which is placed near the first coil. So therefore, they will be coupled. These two coils are said to be magnetically coupled. So these two coils are coupled magnetically, but there is no electrical connection between the two coils. Okay. So the transformer, it helps to transfer energy from one circuit to another. So a transformer is a device which transfers energy from one circuit to another circuit between two different circuits which are not electrically connected but which are magnetically coupled. And it changes the level of voltages from one value to another, and this change of voltage takes place at constant frequency. And this transformer is supposed to be a static device. Static device in the sense that it does not have any moving parts. So therefore, the efficiency of the transformer is generally very high, around surely more than 90, 94%, 95%. Okay. So when there is moving parts, when the machine has moving parts, rotating parts, there will be a friction and windage losses in the machine. So then these losses will reduce the efficiency of the machine. Whereas in a transformer, we have only stationary parts. There are no moving parts. And so the efficiency of the transformer is very high. And in fact, transformer is the device which has the highest efficiency among the AC devices. Okay, so how do we understand the principle of magnetic coupling and the principle in which a transformer is working? So we have, let us consider one single coil. So this is a single coil of wire wound on a iron core. So the iron core is rectangular in shape here. So what happens when you supply AC voltage here, let us say V of T, AC voltage, to the wire, a current starts flowing through the wire, and this current is also an AC current, I of T. So as soon as the current flows through the wire, this will produce flux around the wire. So there will be flux produced in the wire like this, around the wire. So whenever you have a current flowing through any wire, whether it's a DC or an AC, then there will be flux produced around the wire. And in the case of a DC, this flux will remain constant because the value of the DC voltage is constant. Whereas if you supply AC to a wire, then the flux will be changing instantaneously, just like the current or the voltage will change instantaneously. So therefore, this is a flux produced by the AC current, and this is time varying flux phi of T. So according to Faraday's law, whenever there is a change in flux, a EMF is induced in the coil, or voltage is induced, and this voltage is given by N times d phi on dt. So as long as we have this d phi on dt, we have a voltage induced in the coil. So in this coil, we can say that the voltage will be induced. So this voltage will appear across the coil. So this voltage, let us say VL of T, because the coil has an inductance, this is the same as the voltage induced in the coil and given by L di on dt. So we already know that L di on dt is the voltage induced across a coil of wire. Okay, L di on dt is the voltage across an inductor. So this coil is nothing but an inductor. Inductor has a property to develop flux. So whenever we have a coil of wire, that wire behaves as an inductance. Now we also know that the symbol of inductance is like this. So that's why we represent it as a coil. So whenever we have a coil of wire, we have an inductance associated with that, and the voltage across the inductance is given by CL. And this DL, we already know it is L di on dt. Now according to Faraday's law, this L di on dt is the same as N d phi on dt, where d phi on dt is the rate at which the flux is changing. So when you have an AC voltage applied to the coil, the flux is now phi of t, which is changing. So therefore the flux will also have the sinusoidal phase. So if you take the flux can also be represented as a sinusoidal waveform like this. So therefore the value of flux changes at every instant of time, and hence there is a voltage induced according to Faraday's law of electromagnetic induction. So this action is called Faraday's law of electromagnetic induction. Okay. So this is when you have a single coil. Now what happens if we add another coil in the circuit? So this is one coil. So this coil we have supplied a voltage, AC voltage, and this coil now produces a flux around it because the current flows through this coil. This current will produce a flux, and this flux will be traveling through the iron core because the iron core has the capability to transfer the flux, and some of this flux will link with the another coil placed in the same iron core. Now what happens here? We have a voltage, let us say V of t. There will be a voltage, let us say VL of t here. Now under ideal conditions, this V of t equals VL of t. Obviously they will be in opposition to each other, so V of t will be dl of t. Now this flux linking the second coil now, let us say it produces another voltage VL2 of t, because this is another coil L2. Okay, so this produces the voltage VL2 of t, and because of this voltage, when you use this voltage will appear across this coil, and when you use a oscilloscope to measure this voltage, the oscilloscope will give some reading here, and this voltage will also be an AC voltage, and since this current is at one particular frequency, the voltage, the flux is also at the same frequency, and hence this voltage will also be at the same frequency, and therefore we get the same frequency. So this is what is called the transformer action. So in the transformer, by the process of induction, the voltage is induced in the neighboring coil. Is it clear? So whenever you pass a AC current through the first coil, the flux produced in the first coil will link the second coil, and there will be a voltage developed across the second coil. Even though that coil is open circuited, we still have a voltage developed across it. And if you connect a load through this coil, a current will start flowing through the load. So this is the process of induction, and hence it is called the electromagnetic induction. The induction is due to the magnetism flux. The flux only creates the induction process. So therefore, this is called electromagnetic induction. So basically, what is a transformer and the construction of a transformer? What are the main parts in a transformer? So the transformer consists of an iron core. So we have an iron core here. So there are two windings placed. We need a minimum of 2 coils for transformer action to take place. So the coil in which you apply the voltage, the AC voltage, is called the primary coil, and the coil in which the voltage is induced is called the secondary coil. So there are 2 coils, primary coil and secondary coil. They are wound around the same core, same iron core. So we can see here a flux is produced in the primary coil. This flux also links through the core into the secondary coil, and hence the voltage will be developed across the secondary coil. So this core is now made up of many iron layers separated by an insulator. So the aim of this is called the lamination of the core. So this is called lamination. So why do you need to laminate the core? What happens here? The core is also a conducting material. So when you have a winding here, when a AC is applied to the winding, see, these are once again insulated coil. So but still, since we have an iron core, there is a flux, changing flux in the iron core. There will also be a voltage induced in the iron core. This voltage induced in the iron core will produce a current flowing through the iron core. And in order to limit this, these currents are called the stray currents. And to limit these stray currents, we generally laminate the core. So by laminating the core, what we are doing is we are increasing the resistance of the core. So when the resistance increases, the current through the core decreases. So which means the loss in the core will decrease. So that is the purpose of laminating the core. So basically, if you take a transformer, the transformer has three main important parts. One is the core of the transformer, iron core. The other one is the primary winding, and the third one is the secondary winding. And if we can note here, the number of turns in this primary winding, the number of turns in the secondary winding are different. So we could have different number of turns in the primary and the secondary winding. So what is the use of having lesser turns or greater turns in the secondary winding? We will see that now. So what is the principle of operation? To put it in a simple term, the principle of operation is electromagnetic induction. So what we do is here, when you apply an AC voltage to the primary coil, a current, AC current flows through the coil. This produces a changing magnetic flux or alternating magnetic flux, which flows around the ferromagnetic core. Now this changing flux links both with the primary coil and induces an AC voltage. It also links the primary coil, same coil, and induces a AC voltage which opposes the applied voltage. So it is actually VL1 of T, let us say. This opposes the applied voltage which is V of T. Okay, now this changing flux also links with the secondary coil and hence induces a AC voltage in the secondary coil, and this takes place at the same frequency. Now this process is called electromagnetic induction, and this voltage is VL2 of T. Okay, now this voltage at each of the secondary coils, you can have as many number of secondary coils as you want, and it is related to the primary voltage by something called the turns ratio. So the voltage that is induced on the secondary coil depends upon the number of turns in the secondary coil with respect to the compared to the number of turns in the primary coil. So that ratio between the number of turns of the primary and the secondary coil is called the turns ratio. If you connect the load to the secondary, an alternating current flows through the load. Okay, so that means basically in transformer we are having two different circuits which are separated from each other, which are not electrically connected to each other. So we apply voltage to one coil, but we get the output from the other coil. So this is the actual transformer. So this has lot many applications which you will see later. So some figures of transformers here. So you can see this is a laminated core, iron core, primary winding on one side, secondary winding on the other side. This is a transformer which you see in the substations. So this is a tank. This is actually a transformer tank here. So these are actually the transformer bushings, the leads which take out the primary and the secondary connections which are inside the transformer, and these are actually cooling vents. The ones like pins which are protruding there, they are called the cooling tanks or cooling vents. Because it produces a heat, obviously the windings are contained inside a case, inside a tank. So therefore, there will be a lot of heat produced, and so in order to vent that heat out, we have cooling vents. So next is under ideal conditions, we first see the ideal transformer. So under ideal conditions, which is not related to the practical situation, we make some assumptions, so in order to simplify the analysis. So this is a transformer simple circuit. We have N1 turns here on the primary, N2 turns on the secondary. This is a core here. So in symbol we just represent it like one winding with N1 turns, one winding with N2 turns, and this represents what is the core. Okay, so the core is represented by two lines. So this is a symbol of a transformer. So under ideal conditions, we assume that the transformer has no resistance. Okay, so there are no losses in the transformer. Actually, whether any coil, any wire will have some resistance. What is the resistance of a wire depend upon? The length of the wire, or is given by OL on A, area of cross section. So depending upon the length of the wire, the area of cross section, and each material has some conductivity. It depends upon the nature of the material. So every wire will have some resistance R. But under ideal conditions, we assume that there are no resistance in the transformer, which means that there are no losses due to resistance. Whenever you have a resistance, current passing through the resistance will simply produce a heat. And in equipments, in devices like transformer, we are not actually using the resistance for any purpose. Only for example, in heaters and in lights, we need the action of resistor, where in heater, the heat produced in the resistor is used to heat the water or heat the room temperature, increase the room temperature. And similarly, in the case of lights, the heat produced in the resistor, once it becomes red hot, it is transferred into light energy. But when you use resistance in the case of other devices like transformer, here the main function of transformer is to transfer energy from one circuit to the another circuit. So therefore, when a resistance is present, it is going to simply end up in the losses in the form of heat energy. So under ideal conditions, we assume that the transformer does not have any losses. The next one is the core has zero reluctance. So the reluctance is similar to resistance in electrical circuits. In the case of magnetic circuit, we call it as reluctance. Now what is resistance actually? Resistance is opposition to the flow of current. So therefore, we have reluctance is opposition to the flow of flux. Okay, so opposition to flux is called the reluctance, and the core has zero reluctance. That means it allows all the flux to pass through it. The core will not oppose the flux flowing through it. And therefore, to establish the flux in the core, we don't require any current at all. That means the core does not draw any current to produce the necessary flux, to allow the necessary flux to pass through. Next one is, there is no loss in the core due to stray currents. So what is stray currents? I already told you that the currents induced in the core are called the stray currents. Now we assume that there are no stray currents in the core. That means there is no resistance in the core also, and therefore no losses in the core. And next one is, all the flux produced by the primary couples with the secondary. So what is here? When we have a flux produced here in the primary, this flux will travel through the core into the secondary. But you can see here, some of the flux always spreads out in the free space. When you have a conductor, around the conductor there will be a magnetic property present. This is because of the flux present in the conductor. So when you say we have a conductor, the flux also is present in the air around the conductor, in the atmosphere around the conductor. So therefore, when you say that all the flux in the primary links with the secondary, we assume that there is no flux which is leaking out in the air around the conductor. So therefore, there is no flux leakage here. Basically, no flux leakage. This is called flux leakage, and we assume under ideal conditions there is no flux leakage in the transformer. Okay. Now we have something called the turns ratio. We already saw that the voltage in the secondary depends upon something called the turns ratio. So what is the turns ratio? So here we have a voltage by Faraday's law of electromagnetic induction. This voltage V1, which is appearing across the primary winding, is given by N1 times d phi on dt. What is phi? Phi is the flux which is linking commonly with the primary and the secondary. So it is N d phi on dt. So next is, similarly, we can write for V2, the voltage across secondary as N2 times d phi on dt. So when you take this ratio of V2 on E1, so V2 on E1, this d phi on dt is common to both here, so they cancel each other. So we have V2 on V1 is N2 on N1. And similarly, for the current, if you take in a transformer, the power in is equal to the power out. Why do you say that? Because you know, by law of conservation of energy, energy can be neither created nor destroyed. It can be only transformed from one form to another form. So therefore, in a transformer, when you supply electrical energy to the primary, all the electrical energy should be collected back from the secondary. Okay, of course there may be some losses in between in the form of heat energy or leaking flux or whatever. So whatever it is, the energy available does not change. So we see that on the input side we have the total power. With this power, in this case of AC, this is actually the apparent power or the complex power. So the apparent power input to the primary is the same as the power that is taken out of the secondary. So this is apparent power or complex power, which is designated by symbol S. So S is actually given by V times I, isn't it? So therefore V1 I1, which is on the primary, should be the same as V2 I2, and according to that we get V2 on V1 is N2 on N1 from here, and from this V2 on V1 is I1 on N2, and this is called turns ratio N. So the turns ratio of a transformer is N2 on N1. The voltage varies similar to the turns ratio, and the current ratio is the reciprocal of the turns ratio. Now when you go here, we have something called a impedance ratio. So how to find out the impedance ratio? So what we are basically doing is, we have an impedance ZL which is connected to the secondary of the transformer. We are going to find out the value of ZL when it is referred to the primary side. So that is called ZL referred to the primary, which is ZLP. Why do you want to refer that to the primary side? Because we can see here, we have one circuit here, circuit 1, and we have another circuit here for the secondary, circuit 2. So what happens here, when you are solving the transformer circuits, when you are doing the electrical analysis for transformer circuits, you need to solve for two different circuits. And of course, moreover, another point is, we need to also find out the coupling effect in between. We need to have a connecting equation between the first circuit and the second circuit, and this is going to be really complex. So therefore, in order to prevent this, what we can do is, we can draw something called an equivalent circuit of the transformer by transforming all the parameters of one side into the other side. Okay, so in this case, for example, we want to transform the lower impedance ZL into the primary side, and then it is called ZLP, which is the ZL value referred to the primary side. So let us see how to do that. So we have this turns ratio here, which you are already aware of, the turns ratio of the transformer. Next, we know that this ZL, the voltage, the impedance ZL is given by voltage on current. It's simple, Ohm's law. By Ohm's law, ZL is V2 on I2, and then ZLP. Therefore, now what is ZLP? This is the impedance on the primary side. So ZLP can be written as the voltage on the primary side on the current on the primary side, V1 on I1. So now from this ratio, I can write V2 equals V1 times N1 on N2. So V2 equals V1 times N1 on N2. And from this ratio, I can write, because V2 on V1 equals N2 on N1. So I have V2 equals V1 times N1 on N2. And similarly, for I2, I have N2 on N1. N1 equals I1 on I2. So therefore, I can write this I1 as I2 times N2 on N1. So when I take this one, I can write this as V2 on I2, N2 on N1. When it goes to the numerator, it becomes N1 on N2. Already we have N1 on N2. So this becomes N1 on N2 the whole square. So therefore, what is this V2 on V1? We will see that this is ZL. So ZL times N1 on N2 whole square. And we know that N2 on N1 is N. So therefore, this can be written as Z1 divided by N squared. So basically this, when you take the secondary impedance and bring it to the primary side, we basically divide that by the square of the turns ratio. And what is turns ratio? You should always remember that the turns ratio is the secondary number of turns divided by the primary number of turns. So now we go to what is called the equivalent circuit of the transformer. So when you take the equivalent circuit here, we can draw the equivalent circuit showing both the sides. simply just representing the same thing. But then we need to have a coupling equation to write this transformer action. Okay, so therefore what we can do is, here I am just taking this Z2 and then bringing it on the primary side. So on the primary side I have voltage V1, so I write this voltage V1. Now this Z2 I am just transferring it onto the primary side, and we just saw that this can be written as Z2 on N square. Now here this I2, when I have this current I2, this is actually I1 here. So when I2 comes here, it becomes I2 dash. In this case, since it's an ideal transformer, I2 dash and I1 will be the same. But I know that I2 on I1 equals N1 on N2, which is equal to 1 on N. Okay, so therefore I know that I2 dash is N times I2. So when you bring it here, this becomes I2 dash. Okay, so I2 dash now becomes N times I2. Okay, I am referring it to the primary side. So similarly, now on the secondary side, if I transfer everything to the secondary side, you can still, if you want, you can also represent this as current I1. V1 and similarly, on the secondary side, I have Z2, I have the current I2, but that voltage V1 has to come to the secondary side, so that becomes N times V1, obviously, because we know that V2 on V1 equals, this is actually V1 dash. Okay, so we can write V1 on V2 equals N1 on N2. Okay, so this becomes now V1 dash. Okay, so V1 dash now becomes N times V1. So this is how we transfer. Now we can see here, this is a very simple circuit where across an impedance there is a voltage source and a current is flowing. Okay, so it's very simple circuit and it's easier to solve rather than taking that. Now, what is the difference between ideal transformer and a real transformer? If you take an ideal transformer, we have assumed these four conditions. One is no losses in the windings. But in practical transformer, the windings will have losses. Now, how to account for the losses that is happening in the windings? I told you, in devices like transformer, where the main objective is something else, the resistors simply contribute to the heat loss. So the power loss always, and we also know that in AC systems, AC circuits, the resistor produces heat or the power loss. The loss is always in the resistor only. Inductor or the capacitor does not create any real power loss. They cause only reactive power loss. So therefore, when you take loss means it's a real power loss only. So therefore, when you say that the windings have losses, that means we need to additionally add resistors R1 and R2, R1 for the primary winding and R2 for the secondary winding. So next condition is zero reluctance in the core. We have assumed that the reluctance in the core is zero. That means it does not need any current to produce the flux. But in practice, you will have non-zero reluctance, and therefore there will be reluctance is a term associated with the magnetic circuit. So it is always related to inductance of a coil, or we know that X is called the reactance of the coil, which is given by omega L, J omega L. Okay, so inductance and the reactance are linked by this equation. So therefore, we need to add a reactance Xm for the core. And then next point is, under ideal conditions, we have taken that there are no losses in the core. So in practical situations, the core will have losses, and once again, the losses are now associated with the resistance. So we include a resistance Rm for the core. Next is, we have assumed that there is no flux leakage. So this is what is called the leakage flux, the flux that is leaking. See, there are two lines of flux shown here which goes through the core. There are some flux which are free here on this side and on this side. This is called the leakage flux. So what happens whenever you have a leakage flux, then once again there is a loss of flux, isn't it? So this loss of flux can be represented in terms of reactances X1 and X2 present on the primary and the secondary side. So therefore, in practical transformer, there is flux here. So this is what is shown here. So there is flux, and what we do is this part of the transformer represents only the flux that is linking with the core, and whatever flux that is leaked out is represented by two reactances or two inductances, X1 and X2, connected on the primary and the secondary side. So if you take the practical circuit, now what are the things that are added in the practical circuit? These are the parameters that are added. One is the resistance R1, R2, then the inductance X1 and X2 in the primary and the secondary winding, and in the core we have the resistance Rm and inductance Xm added. So the core, both the coils and the core, which are the three main parts of the transformer, all have a resistance and inductance added to them in a practical transformer. So how will the transformer circuit look like? Okay. Going somewhere. So we can take it one by one. So practical transformer, therefore, we have the ideal transformer which is given in the center. Okay, so this is an ideal transformer. Now on the primary side, we have a resistance R1 which represents the loss in the primary. Then we have the inductance X1 to represent the leakage flux in the primary, and similarly on the secondary we have an inductance X2 which represents the leakage flux in the secondary, and a resistance here R2 which represents the power loss in the secondary. Now these two are two separate circuits. Now apart from that, for the core we have the inductance and this one. So on the core is actually available on this side. So sometimes to approximate this one we put it here. So we have a resistor Rm for the core, and we have a reactance Xm for the core. So this part now represents the core. So we apply a voltage, say V of t on the transformer, let us say, because it is applied to the primary side V of t. So this part now represents the core of the transformer. This part represents the primary winding. This part represents the secondary winding, and the center part now represents the ideal transformer. So this is what is a transformer circuit for a practical transformer, real transformer. Okay. So the same thing here, some of the flux produced by the primary winding. So you can see here, this part usually the core comes near the winding. So under approximate conditions, this can be put here on the other end. So this will be the circuit of the transformer. So this represents, as you have seen, this represents the core. This represents the primary. This represents the so this is the equivalent circuit. Now approximate equivalent circuit. What is an approximation done here? The branch which was here has now moved near the source. This is in order to simplify the analysis. Actually, we cannot simply move it from this side to this side, but we have moved it here and approximated the equivalent circuit for the simplification of transformer circuit analysis. And now another thing we have done is Z2 was on the secondary side. Now this is referred to the primary, this circuit. So it becomes Z2 dash, and R2 and X2 become R2 dash and X2 dash. The current flowing through the secondary now becomes I2 dash. Now there is the current I1 which is drawn from the supply into the primary. There is another current I0 which is drawn by the core, because we have seen that when the core has zero reluctance, that means it does not take any current to produce the flux, but the core under practical conditions has non-zero reluctance, and therefore it will obviously draw a very small current, say I0, in order to produce the necessary flux. So therefore we have I0 here. So if you see here, actually we can see by applying Kirchhoff's law at this point, I1 will be equal to I0 plus I2 dash. So this will be the simple equation when it is referred to the primary side. Now we can also refer it to the secondary. So when you refer it to the secondary, we keep Z2 the same, I2, R2 and X2 here. Now this R1 becomes R1 dash, X1 becomes X2 dash. Now all these becomes Xm, the current becomes Im dash. In fact, this becomes Xm dash and the resistance becomes Rm dash. In here it is given as Rc1, we can also take it as Rm. So this will become Rm dash. And the corresponding current will be, this is Im dash. So this becomes, say, IR dash, whatever. Okay. So this will be the equivalent circuit referred to the primary or the secondary side. Now what is the meaning of this Z2 dash and all? So when you eliminate the transformer, reflect the secondary circuit onto the primary side, the general rule is divide the secondary impedance by Z square, divide the secondary voltage by N. So whenever you want V2 dash, divide V2 on N, and then multiply the secondary current by N. So this is the general rule for transferring the parameters from secondary to the primary side. Now in this case, the rule for eliminating the transformer and reflecting the primary circuit to the secondary is multiply the primary impedance by N square. So if you divide it, when you transfer the primary, you just do the opposite thing, multiply by N square, and in this case you have divided by N on N. So in this case you have to multiply by N, and then in this case for I2 dash you have multiplied by N, and for I1 dash you divide by N. So you just do the other way around. So it's enough if you remember one value, and for your examination it's enough you know the concepts. You will not get problems based on this transformation. Now what are the applications of transformer? So the transformers find applications in something called as an isolating device. So isolating the DC and the AC part of circuit. So whenever we have rectifier is a device which converts the AC to DC. So in the case of rectifier circuit, we need a transformer which will reduce, because rectifiers usually operate at very low voltage. For example, the examples for this applications are mobile phones, PCs, or electronic gadgets that you use, okay, iPads, whatever. So what happens here is, these devices use only DC. Now we have only AC in the house, the power coming into the house is AC. So therefore that is 240 volts AC. So you convert that 240 to DC, and that DC voltage is also at a very low level, say around 9 volts or something. So what happens here, this will be, for example, 240 volts AC. So this will be actually AC 240 volts AC here. Now this AC will be converted by the transformer, say to 9 volts AC, and then it will be fed to the rectifier, and output of the rectifier will get 9 volts AC. So that's why the chargers for mobile phones, they have a thick region there, it has a small transformer inside. So therefore transformers are used as isolating devices. Next is matching devices. So matching devices in the sense, whenever we want a speaker, we are using devices like speaker, we need a very low voltage. So therefore it converts the voltage from one value to the other value. These are all smaller transformers. So it's called impedance matching actually. To match one circuit to the other circuit at different voltages, we need a transformer to isolate them. Another thing is for power distribution. This is the main important application used where you see very big transformers near the substations and on the poles. So what we have is generators. Usually the generator voltage is quite small. In this case, this is shown for the US standard, so it's around say 18 kV here. So this voltage is stepped up to high value of 345 kV, and this voltage is transmitted. So the power is transmitted at this high value of voltage. Why do you want to transmit power at high voltage? So when a power is transmitted at high voltage, electrical energy is transmitted at high voltage, it's seen that the losses are comparatively lesser. when power is transmitted at high voltage. So therefore, the power here is transmitted at high voltage. And what happens here, what you are using at home is a very low voltage. Okay, so 240 volts in Australia. So therefore, what happens here, you cannot use this voltage. So at the distribution side, we use a step down transformer which steps down the voltage to the value that is used by the consumers, and then it is distributed to the consumers at that voltage. So in this case, it is 208 volts. This is 3-phase for a US system. So 3-phase 240 volts is actually single phase voltage. Now in Australia, if you take a 3-phase voltage, it's called something around 440 volts. Okay, so that doesn't matter. So what matters here is the transformer is used in power transmission and distribution. Mainly, we use two types of transformers. These are called power transformers. We use step-up transformers on the generation side to increase the voltage to very high value when the power is transmitted at this high voltage. And on the distribution side, that is in the substation, we use step-down transformers and then feed that lower voltage to the consumers of electricity. So what happens if you supply a DC to a transformer? Now, we could as well say that it will not work, but more than not working, it will harm the transformer or the equipment will fail basically. What happens here? So when you supply a DC to the transformer, what happens? Still, whenever a current flows through a winding, it will always produce a flux. So in this case also, there will be flux, but there is no change in flux here. The flux remains constant. Because the DC voltage is constant, the flux is also constant. So the flux remains constant and hence no voltage is induced. Because we know that for voltage induction, we need to have d phi on dt. So what happens with the DC? This d phi on dt becomes 0. So therefore there is no voltage induced in the coil. So when there is no voltage, that means the whole applied voltage is dropped across the primary resistance only. So we have a primary, let us say, theoretically speaking, a primary consists of R1 and X1. And there is a ideal transformer here. So we supply a voltage here, say D1. So we also know that under steady state conditions, the inductance behaves as a short circuit. So when you apply a DC voltage, the same circuit can be drawn like this. So this is DC voltage. So we have only resistance and then the inductance behaves like a short circuit. So what happens here? There is only resistance R1. So that means the whole voltage now appears across the resistance R1. And usually the resistance of the transformers are made very low because we know that the resistance of a transformer is just going to cause only power loss in the form of heat. So we want to reduce that. So generally the resistance is kept very low. So what happens when you have a lower resistance and a high voltage applied across this resistance, the current flowing through will be very high. Suppose I take this is current I1. So I1 will be just I1 on R1. So therefore when this is going to be low, this is going to be high. Okay. So therefore a very high current will pass through the primary winding and this will burn up the winding. So it will be more than the current that the winding could tolerate. So therefore, very high currents flowing through the primary winding will burn up the primary winding. So this is a problem when you apply a DC to a transformer. Now let us do a few problems in the transformer here. So here in this case, the input voltage is given as 240 volts. Okay. So we need to find out the turns ratio here is given 12:8. That is N1 is 12 and N2 is 8. So what we can do is we need to find out the current flowing through this capacitor. So in this case this is the secondary current, let us say I2. So in order to find the secondary current, this is an ideal transformer. There is no primary resistance, secondary resistance, etc. So let us say this is the voltage in the secondary, which is V2. So we know V1. So we have here V1 is 240 volts. We have N1 equals 12, N2 equals 8. So how do you find V2? Only related by turns ratio. So I can write here V2 on V1 can be written as N2 on N1. Okay, so this is the turns ratio. So I can write directly V2 equals V1 is 240 times 8 on 12. So this will be the value of V2. So this works out to 160 volts. Now once we know V2, how do you find X2, I2? Now we need to find out what is X2. Because this is a capacitor. So what is X2 for a capacitor? Minus J on omega C. You know that? So this one becomes minus J. What is omega? 2 pi F. So 2 pi times F is 50 Hertz and the capacitor value is 5 microfarad. Okay, so therefore we get the value of minus J 636.62 ohm. So we have converted that farads to ohm. So that means we have converted the capacitance to capacitive reactance. So once we know the reactance, now what is I2? Now it all becomes a vector. So I2 becomes V2 on. So what is V2? Now in this case, we can, since there is no angle associated with V2, I will take this as a reference. So I can take it as 160 at an angle of 0 divided by minus J 636.6. So the answer I get is J 1251. So this will be the current through the. So what I have done is simply follow the turns ratio, the relationship between the turns ratio. Next question here. So the transformer here has a load connected to the secondary. So what are the data given here? I2 is given, V2 is given, and cos phi 2. Cos phi 2, the power factor on the secondary side is given. The transformer R1 is given, R2 the secondary voltage and the turns ratio. So N1 equals 20, N2 equals 1. And we need to find out the voltage applied on the primary side. So you are asked to find out what is 1. So this, therefore, now this is a transformer. It's not an ideal transformer. It has resistances R1 and R2. But there is no mention of the reactances X1 and X2 or Rm and Xm. So we need not bother about that. So how will you draw the equivalent circuit based on this? So the equivalent circuit will have R1 and R2 connected in the circuit. So let us come back to this. Okay. So let me draw the figure here. So we have a transformer with a resistance. Okay, and then the secondary is here, which has only resistance, and then there is a load. Okay, so the current through the load and the current through the resistor are one and the same. Now what are these resistance values? Sorry, I'll just draw it neatly here. So we have resistance, primary, we have secondary, and we have resistance. That is the load. So this is the circuit. Now this resistance is how much? This resistance is 50 ohm. This resistance is 0.05 ohm. Okay, the current here is given as 4 ampere. The voltage across this load is given as 12 volts. Now we need to find out what is V1 applied. Okay, so in order to find that, we need to find out the turns ratio is of course given, which is given as 20:1. Now how do you solve this circuit? The current is the same here. The same current 4 amperes flows through the resistor also, because the load and the resistor are connected in series. Now we need to know the angle at which the current varies. Now what is the other information given? Cos of phi 2 is equal to 0.5. So therefore what will be phi 2? Phi 2 will be cos inverse of 0.5, which works out to 60 degrees. Okay, now it also says that it is lag. So what does lag mean? What is the power factor? Power factor is the angle between voltage and the current. And if you say lag, that means the current lags the voltage. So therefore, we can draw it like this here. The voltage V2 will be here. The current I2 will be lagging the voltage, and this angle is 60. So therefore, let us take here as V2 as reference. V2, let it be taken as a reference. So we always need a reference vector in AC calculations. So once you take V2 as a reference, let me rub this off. I have space here to write. Okay. So what we have is, we have V2, which is given by 12 at an angle of 0. Therefore, we have now I2 is 4 at an angle of minus 60. Because I2 lags the voltage by 6 degrees, so I put a minus there. So this is more than which is minus. So next is, I have, sorry again, here let us draw the circuit here. Okay, this is the load. So what happens here, this voltage V2 is the voltage across the load, but we want the voltage here at this point, which will be naturally different. So let us take this voltage as Vx1 and the voltage across this winding as say Vx1 and this one as Vx2. So what will be Vx2 now? Vx2 is this voltage across this load plus the voltage drop across the resistance. So what is the voltage drop across the resistance? The same current I2 flows through the resistance R2. So this is V plus V2. Now all these are vectors, of course. So therefore, I can substitute here. I2 is 4 at an angle of minus 60 times what is R2 is 0.05 plus what is V2? V2 is 12 at an angle of 0. So I can compute this to find out what is Vx1. So therefore, Vx2 now works out to 12.1 minus J 0.17. So this will be the value of Vx1. Now, once we know Vx1, we can find Vx2. So we can find out Vx1. So what will be Vx1? Vx1 is depending on the turns ratio. So Vx1 will become Vx2 times 20. The turns ratio is 20. So therefore, this is 20 times Vx2. So therefore, I get a value of Vx1, which comes to 242 minus J 3.4. Now I have Vx1, I know R1. So now what will be the current here? I know I2, so I can find out I1 once again based on the turns ratio. So I1 will be I2 on 20. So this will become 0.2 at an angle of minus 6. So I know the current, I know Vx1. So therefore, just from that circuit, I can write the input voltage V1 will be I1 R1 plus Vx1. All these are of course vectors. Now I know the value of I1, I know value of R1 and Vx1. Of course, they are all complex numbers. So once I solve this, I get this as 200.3 at an angle of minus 2.8. So this will be the voltage that has to be applied on the primary side in order to supply the necessary current and voltage to the load. Okay, now this is again a simple problem. So how do you draw the circuit? The transformer in an electric piano. So there is the electric piano in the transformer. So therefore the load to the transformer is a piano. So it reduces the 240 volts to 12 volts AC. So what happens here? We have a transformer. Okay. So this transformer, now the input to this is, there is no mention of resistance or whatever. So we can simply ignore that. So this is a 240 volts input. And then we have the output of the transformer is 12 volts here. And we have a piano acting as a load to the transformer. Okay, so this is the simple circuit. Now the turns ratio, we have given, the current through the piano is given 500 milliampere. Okay, and then secondary coil has 30 turns. So N2 is given here as 30. Now how many turns are there in the primary N1? Okay, so what you can do is, we know the secondary current and the voltage, so we can simply use the turns ratio. So what is the voltage here? Voltage is given here. We know that V2 on V1 equals N2 on N1. So what is V2? V2 is 12 volts and V1 is 240, N2 is 30. So therefore only unknown is N1. So by using this equation, we can get N1 to be 600. So this one. Now the current in the primary coil, we know the current in the secondary and we know the turns. Therefore we can write, we know that the current in the primary is given by I1, I2 equals N2 on N1. So N1 is known, N2 is known, I2 is known, therefore we can find out what is I1. So I1 here works out to 25 milliampere. And what is the power output of the transformer? You know the power, for a transformer we take only S. Because if we want the power output, in AC we have 3 powers, SP and Q. And if we want the power output in terms of active power, we need to know the power factor. Since there is no mention of power factor here, we can calculate only the apparent power V, S, which is given by V1, I1, or it is the same as V2, I2. Now all these values are known, so you can either find V1, I1 or V2, I2. So this power works out to 6, and the unit of this apparent power is volt ampere. So 6 volt ampere. Okay. So in summary, what is a transformer? So transformer is a device operating with AC, and it helps to transfer the power from one circuit to another without the change in frequency. And it is basically used to convert AC power at a certain voltage to AC power at a different voltage level, but it takes place at the same frequency. Okay, thank you.